8 asks, given a perimeter of 48 feet and a height of 12 feet, what is the surface area of this figure? Leave as an exact answer. That's typical if we have a hexagon because we do have 30-degree angles and 60-degree angles involved. And they say this is a regular hexagonal pyramid. So what we know is that our hexagon at the base, it's regular, meaning all sides are equal, all angles are equal, there's symmetry everywhere. So we'll go ahead and dive right in. Your typical, for a pyramid, your formula is going to be, let me switch to blue here. It's going to be surface area equals the area of your base, not equals, plus. So area of your base, and then they want the area of the lateral sides. We have 6 sides that go to a point, right? To a common vertex there. And that formula is 1/2 perimeter times L. Now, L is actually the lateral height here, which extends from the vertex all the way down that flat side, okay? So it's, again, lateral. Think lateral is your side, extends from the top at the vertex all the way down, and it creates a right triangle, and of course, cuts that isosceles base in half. But back to our formula here, I do need to figure out what B is, because the area of your base, that big capital B there, is actually, we'll need to substitute that. We'll need to say, okay, it's 1/2 AP plus 1/2 PL. And you can actually make your life a little easier here and factor out the 1/2 and the P to have A plus L. All right, so do we have any of these? We do have a perimeter. Okay, so we can actually substitute 48, right, for our perimeter. So I'll just put P equals 48 up here. And so here's where we need to actually do a little bit of work here. I need to find my apothem of the base, that base hexagon, and I need to find the lateral height. So we need to do some good old trigonometry here. Now, just to clear up this figure here, I'm gonna go ahead and erase that. And first we'll tackle the apothem. So we do know the height. We do know the height of this particular pyramid. So we know it extends from the top here and it goes all the way down to the center. Okay, a little bit different. It's gonna, right below it, it's gonna go straight down to the center of the base of that hexagon. And we know it's 12. I'll tack it at 12 here. Now I could, let's see here, how could we find the apothem? Yeah, you know what? I think we'll need to find the apothem first and then go for that lateral height. Yes, yes, yes. All right, so we're gonna have, I just had an epiphany here. Yeah, because, yeah, I'll show you why here in just a moment. Let's work our way backwards and figure out, based on our perimeter, we can use our perimeter to figure out what our apothem is on our hexagon. So if we have a perimeter of 48 feet, we know each side, if we take 48 and divide by 6, I know each of these is 8 total. And I know if I cut that in half, I have a side of 4 here and 4 here. So on each side I have 4. And then what I can do is I can use some fancy trigonometry and figure out what my apothem is. So I'm going to go ahead and write up this base here in sort of a 2D fashion. Okay, so again, we're gonna have 6 equilateral triangles in this hexagon. And to find the central angle, we'll just divide by 6 from 360. Okay, so it's 360 divided by, I don't know what my pen is doing there. All right, so 360 over 6, that's a central angle of 60. Aha, right? Yeah, 60 degrees. So I know I'm dealing with the 30, 60, 90 situation. Let's break it down even more. So I do know this particular angle is 60 degrees, but I want to look at one of those right triangles. We have one on the left and one on the right. It really doesn't matter which one you're looking at, but we'll go ahead and do that. We'll just do the right hand side. And I'm looking for A, right? I'm looking for apothem. Okay. And we'll use apothem to finish out our right triangle situation. We'll see here shortly. Now, A is going to be, we're going to find that out. We know this is 4. Remember, I just cut each triangle in half. This is 4 and this is 4. We'll have a total of 8 as our side length. We just pulled that from the perimeter. Now, if I know the central angle is 60, going right 60 here, and I would just need to break it down. 60 over 2 would be 30 degrees. So each of these angles within, inside the individual right triangles are going to be 30. Okay, so always remember, if you're trying to break down for area purposes, if you're trying to find the apothem or maybe the side length, you need to take that central angle, just take 360 and divide out by however many sides you have to get the main central angle, and then you just cut it in half because you're just going to look at one separate right triangle from the individual triangle you just created. So we have a 30, 60, 90 situation, right? And so we need to know our ratios for sure. So I do know that we have our opposite side. We have our 4 part of our side length, but we do need A. We do need A. So remember, whenever we have a 30, 60, 90, okay, we can call this okay. So we have these ratios we need to consider. So if I have the shorter side, I know the hypotenuse is double that shorter side, and then we take the longer side times √3. All right, so we have the side opposite of a 30-degree angle, the shorter side. We know it's 4. I do know this is 8 over here. I'm going to put 8 on the hypotenuse, so it's not relevant. We don't need it. And then A is just going to simply be X, which is our 4, 8, and this would be 4√3. All right, 4√3. So A has to be 4√3. Okay, this is a lot of finagling to get this value, but again, we just took our central angle, broke it down to the angle of one of our right triangles, and then I'm going to find that apothem. Our apothem is now 4√3, and I used what I knew or know about our 30, 60, 90 triangles and what those appropriate ratios are. Remember, the short side, the side opposite of 30, is always half of the hypotenuse. And then you can just take the length of the short side and multiply by √3 to get your longer side, or the side that is opposite your 60-degree angle. All right, hopefully that helps there. Now I do have A. I officially have A. A is going to be 4√3. What else do I need? I need that lateral. I need that lateral side here. Okay. I'm going to go ahead and show this over here. Bear with me. I'm going to go ahead and write. I'm going to show another right triangle we're going to create from the height. So we're going to extend that height down again. We do know our apothem, right? Our apothem is going to go here. Remember, we have apothems extending out to each, from the center of the base to each side. And I'm referencing the one to the right so you can see it from the side and see it better. And then last but not least, we have that lateral height that's extending up from the middle. Okay, so we're going to use, and this is a right triangle. Okay, it's sort of embedded in there. So we have this right triangle here. It's made of height, the height of the pyramid, the apothem, and then extends up to the lateral height. So we call that HAL, actually. Thank you to Highland Park. They have there are about 3 different right triangles that we can use here. This is how. And just for reference, you can also use, I'll write them down here, how, her, I think it's less. Okay. So depending on what information you're given, you can use these right triangles. How is, again, height, apothem, lateral height. Her is height, edge. That's this guy right here. I'll write that in here. That's edge right here. Or we're not using it, not relevant to this problem. And then R is going to be your radius. That's, again, radius extends from here to here. Okay. And then less is lateral height, edge, and S would be side length. So that would be here to here. Yeah, we could do the edge, and edge is right here, and then extend down that lateral height. So you do have this is really kind of neat. You have 3 different right triangles that you can maneuver and use to your advantage when you're working these types of problems, especially when you're having missing information. But, and again, her and less are just, those were just bonus. I'm going to go ahead and delete that here. That's just bonus information. But we're using how. Okay, so we need to actually to find our lateral height. We know, and that's our question mark, right? We'll just call this maybe X. We know apothem is 4√3. And we know our height is 12, the height of the pyramid. All right, so it looks like we have our 2 legs. And so I'll go ahead and square 12 and square 4√3 equals c squared. And that would be 144 plus 16 times 3, that's 48. I wonder what kind of result we'll get there. 144 plus 48, that's our 192. And I imagine, oh, is that a perfect square? I don't think that is. I think 196 is a perfect square. Yeah, 192. So 192 is 64 times 3. So that'll reduce to, okay. So we know our C value we found is actually our lateral height here, our L, and that is going to be 8√3. All right, so we're almost done. We just got to substitute. Given that information, we have perimeter 48, A is 4√3, lateral height is 8√3. We'll go ahead and find what our, ultimately we're looking for surface area again. Sometimes you forget, like, what am I doing? And that's why it's really, really important to put your formula out there so you can keep track of what you need. All right. So ultimately I figured out, okay, I have 1/2 P and then in parentheses A plus L, I need to hunt down A and L. Once I have those 2 additional pieces, I can figure out what my answer to the problem is. So if we take 1/2 perimeter times A plus L, we'll have, and don't expect these to be pretty. These could be kind of nasty. Actually might not be bad. Yeah, we have 4√3 and 8√3. So 4√3 and sorry about the noise there. 1/2 of 48 is 24. And if we add, so 4√3 and 8√3 truly adds up to 8 plus 4 is 12√3. Almost there. What's 12 times 24? Ultimately, that's 288. So 288√3. Wow. And that was feet squared, wasn't it? Yeah. That was a long one, but thanks for hanging in there with me. Hopefully you were able to follow this. If you have any questions, please let me know, and see you in the next video. Thanks again.